thank you also to the other speakers and everyone who's sticking around. It's been extremely thought-provoking conference so far. Yeah, I was worried people wouldn't get the... Oh, that's not working. Yeah, okay, no, it's fine, it's fine. I was worried people wouldn't get the joke that I was trying to make pragmatism more realism friendly. So that's the significance of the coloring. So much like Wendy, I guess I'm going to apologize in advance for giving a very big picture, kind of programmatic-y kind of talk, I guess. But unlike Wendy, I can't say I've been thinking about this for 10 years, unfortunately. It's a bit more recent, although it is in some sense the outcome of a fairly long conversation with a couple of other people who are worried about measurement in particular, and about the epistemic implications of measurement for general questions in philosophy of science. And I'll be kind of talking about some very recent stuff so recent it hasn't even been published, which means I can attribute any view whatsoever I want to my interlocutors. But I will explain it all, so it will be transparent and intuitively plausible, I hope. I made perhaps the tactical error of appending the word transcendental to my own positive view, which you can just stop your ears if it starts to rub you the wrong way. Yeah, no, I know, it's terrifying. Yeah, you can call it transcendental sub non-K or something if you want. Okay, so how does measurement connect to the theme of this conference, models and representation? I'm afraid I'm going to give a talk where I won't be using the word model or the word representation very frequently. But there is a very close connection, I think, to lots of the questions that we have about both models and representation. And so really, rather than talk about a particular sort of modeling, I'm going to talk about what happens when you think about the role of modeling in measurement. And it's, I think, generates a certain sort of epistemic puzzle that I, much as in the realism debate more generally, the kind of recent history has been people trying to find the right sort of middle ground between the poles of realism and anti-realism. I think in the case of thinking about measurement outcomes and what they tell us about the world, what they represent about the world, there's kind of a tension between more realist and more anti-realist tendencies, and I want to find a way to be just a hair bit more realist than the people that I'm in conversation with, who are just a little bit too anti-realist for my own tastes. And I hope the question of representation is clear here, because I think in many respects, certainly the classic way of thinking about measurement is as a way of representing physical values through numbers or something like this. And insofar as we think that our scientific theories are about the world in some sense, then measurement is a way that we kind of make contact with the world and show the extent to which it does. So the kind of background question for all this is, what do our measurement outcomes tell us about the world? And in particular, if it looks like we're being successful at measuring in some sense, and then kind of what that means to be successful at measuring is one of the things we'll talk about, what does that allow us to believe or infer about the world? Can we say that these measured values are veridically representing objective properties in the world? This is the background context of things. So I'm going to start with a very naive view of how this might work, of how measurement might make contact with the world and its position within philosophy of science, not necessarily because anybody has held this naive view, but as a way of motivating the less naive view. So here's what you might think if you just kind of stumbled in out of the wilderness and saw scientists engaged in their practice. You might think that measurement outcomes are somehow epistemically basic. So there's something out there in the world, and I hold my measurement device up against it. I lay my ruler against this table. I hold my thermometer up against a pot of boiling water. That device indicates some value. There's a number I read off it, and this value tells me something about the state of the world. And then there might be all kinds of further epistemological problems for science, right? So maybe I've got some sort of theory about the underlying unobservables that are generating this measurement value, but I might think that value, that thing I read off the measurement device, is the starting point for all of that reasoning. It's somehow impervious to those kinds of worries. So whoops. So here's a sort of diagram of how this might, very naive view might go. There's some sort of underlying unobservable causes, and they somehow physically interact with the measurement instrument, and then it just kind of indicates something. And then maybe we have all kinds of interesting philosophy of science questions about how we do statistical analysis over the measurements we make, and we have theories, and maybe there's some question about how does our data support our theory. Do we need to perform any sorts of inductive inference or inference to the best explanation? Maybe our theory is representing patterns in the data. And then maybe there's some further realism debate about how, what our theory says about these unobservable causes, what it licenses us to believe about them. So this is a very naive picture. If it doesn't sound naive, then that's fine. It'll get even less naive later. And the point of talking about this is on this kind of naive view, the measurement process itself is somehow insulated from all the stuff that's going on the theoretical side of things. And that's what allows it to play this role of being epistemically or somehow evidentially basic. And then you can add lots of talk about models into your sort of philosophy of science while still leaving this naive view about the measurement side of things. So you might worry that, well, there's this interesting thing, models that are different from theories, and they kind of coordinate or mediate between theories and the world and the data somehow, but that might all be separate from what's going on with the measurement process. Okay, so this is like a naive first pass starting point. And the crucial point to note, the point that's going to become problematic here in just a minute, is that on this very naive view, the outcome of the measurement is essentially just an observation in kind of the classic early 20th century sort of sense, and it can play this role of being epistemically basic, and it's everything else that's problematic and worrisome. And on this view, you may even have worries about error in measurement somehow, but they're not worries about this kind of physical interaction between the device and the world, but they might be worries about human error, or your thermometer is broken, or whatever. Okay, so moving past the naive view then, what's happened in the relatively recent past, or at least people have kind of drawn our attention to in a way that it was insufficiently drawn before, was the role of models even in these kind of earlier, most fundamental steps of measurement. And that's kind of driven some people. I'm going to talk in particular about Iran Tal and Ha-Seok Chang in the direction of a form of coherentism. So how is this supposed to work? Well, the idea was actually maybe even this initial step of looking at numbers on the measurement device and having some number that we take as our measurement outcome, maybe even that is somehow mediated by modeling. So, for instance, we need to do all sorts of error correction. And maybe we're not just worried here about human error, but we're worried about systematic errors in our measurement devices and how to deal with those. We're also worried about perhaps calibration, ensuring that lots of different measurement devices are doing the same sort of thing, are agreeing with each other. And in order to do that, we maybe need to model things about the measurement devices themselves in order to make comparisons. Then there's also questions about this interaction that happens between the measurement device and the target system. So if what we're trying to do is assign some number to the state of the world, maybe it's not just the case we read that off what the measurement device is doing. Maybe we need to model something about the interaction between the measurement device itself and the physical system it's interacting with. And we may even need to go so far as to model hypothetical physical states that go beyond the ones that are there when we hold the device up against it. So I'm thinking here in particular about some work that Iran Tal did. We have the boss of Iran Tal in the room, so I should be careful about what I say. Yeah. No, I'm a fan of Iran. This is a pro-Iran Tal talk. So an example that Iran Tal has explained in detail to kind of drive this point home is the way that the measurement of time works in contemporary physics. So with the reform of the metric system, the kind of basic physical constants no longer, in most instances at least, are tied to particular objects. They're now tied to sort of fundamental physical processes. So in the case of time, the second is defined as 9,192,631,770, or thereabouts, period of, what does this mean? Hyperfine transition of outermost electron of cesium-133. So the basic idea is a cesium-133 atom, if you have it at absolute zero, it's got a single electron in its outer energy shell, and that electron oscillates between two different energy states at a regular period. And so the number of oscillations is then tied to this thing, the second. And this is how atomic clocks or measuring time and the kind of the standard of time that serious physicists use is tied to this behavior of the cesium atom. I resolutely decided to continue spelling cesium the American way, despite it being spelled the British way in Iran's paper, because that was in BJPS. But, you know, I've got to add a little bit of myself into these things.
Also because Canadians use the British spelling.
Oh, do they? Oh. He's not really Canadian anyway. Why might this example problematize this naive view about measurement? Well, there's models all over the place here. I mean, so one thing to point out is you're not actually able to take these cesium atoms and bring them to actual 0 degrees Kelvin. You get them as close as you can, but that's a theoretical limit. So you're having to kind of move beyond the actual state of the system you're investigating to this kind of, you're having to extrapolate to this hypothesized physical state. There's also serious questions about the way the detection is interacting with the atom. Actually, I don't know that Iran mentions this, but you might worry about this sort of thing. The actual physical interaction between your big old metal atomic clock there and what's going on with the outermost energy shell of the electron. And then one of the things that Iran has gone into great detail to kind of help the rest of us understand is the way in which no one clock is taken to be the standard for measurement here. So there's no like, here's the good clock, and then we calibrate all the other clocks by it. Rather, there's a whole bunch of different cesium clocks, and there's this really quite elaborate process of iteratively weighting them and taking the average across them all as the kind of what we mean by universal time, the kind of the physical standard for time at any given moment. And that's this ongoing dynamical weighting process, this constantly being corrected such that no one clock has authority. So here's Iran talking about this in the Dugald-Stewart building just across the way. I actually thought maybe at one point this conference would be in that room, and then I was gonna try and do like an Iran pose like in this very room, but it was not to be. I was reminded that this is a screen capture, so you can watch him talking about this very thing on YouTube if you're interested. But I was reminded that this talk had been recorded and found it because I was looking for his slide, but attention away from Iran towards this slide. He's trying to schematically show this process where what you have here are a bunch of different atomic clocks, and you make sort of local approximations across averaging them, and then you average those things. And so the coordinated universal time, which is the kind of the gold standard for a measurement of time, is not tied to any one thing. It's this complex statistical modeling weighting across all these different clocks. So that's the point of the example. Okay. So here's an attempt at a kind of heuristical diagram of something like the Iran-Tal view of measurement as a kind of contemporary practice in physics and the roles that models play. So we've got some sort of object or event in the world and the measurement instrument, and there's some complex physical interaction going on between them, and we need to do some sort of theoretical or statistical analysis of that. So that's sort of one role of building models. Yeah, these measurement instruments, they are spitting out numbers of some sort, but those numbers are not something that we ever kind of naively take to be playing some foundational epistemic role. Instead, we need to use the modeling that we've done of this instrument system interaction in order to appropriately weight and correct these indications. And the way that you can see that this sort of picture about how measurement works is going to problematize this sort of very naive view about the epistemic role that measurement outcomes play in science is that, of course, where are these models coming from? Where is this theoretical analysis of what's going on with the measurement system interaction? Well, it's tied into theoretical assumptions about what's going on in the physical system. I mean, I have, if I'm a physicist, all sorts of theoretical views about what kind of thing a cesium atom is and what's going on with the electrons in the outer shell. And there's going to need to be some kind of coherence or interaction between those background theoretical assumptions and the models that I build. They're going to inform how I analyze the device. So there isn't this kind of one directional flow of information, right? On the naive view about measurement, there's the world and it's just kind of spewing information at us, and then we're kind of struggling to infer its underlying states by building our theory. There's actually this kind of feedback loop of us taking our theoretical assumptions and using them to improve and change our measurement devices and to analyze the numbers that are coming out of those measurement devices. I don't know if this is how Iran would diagram this, but I did send him this diagram, and he didn't say, no, that's not what I think. So I'm going to take that as, yeah, I mean, it's rough. And I left lots of things out. You should read his paper, because it's really detailed and fantastic. And he's written about it several places. Okay, so what's the upshot of this? Well, I think one way of thinking about the upshot of this view for both Iran and some of the other people who've been looking at measurement practice in this level of detail is as motivating a form of coherentism. Where coherentism in what sense? Okay, so we no longer have this one directional flow of information from the world. We can no longer have this naive view once we recognize that the way that measurement depends on models. But what we can do is look at how this practice, this iterative practice of improving our measurement devices on the basis of our theory and then letting that kind of feed back into our theory and refine our theory, we've got this some kind of iterative process there, and we can talk about increasing the coherence within that process. And maybe it's this increased internal coherence across theoretical and measurement practices that's kind of driving progress in measurement as a means for developing scientific theory. I want to now, I mean, it's a little bit unfair to group them together, but I think the views are relatively close. I want to make contact here between the detailed work that Iran has done on time and some of the things that Ha-Seok Cheng has said. So Ha-Seok Cheng is someone who's also looked at measurement. He looked at it in the case of the history of thermometry in his first book. He's more recently looked at it in other aspects of the chemical revolution. And he uses this term epistemic iteration. So what does he mean by epistemic iteration? There's some sort of iterative procedure for refining knowledge claims. And so you do build on previous stages, and there is supposed to be some sort of notion of progress here. But the progress is coming through this kind of internal back and forth between theory and measurement practice. So here's a quote from Ha-Seok. Iteration provides a key to understanding how knowledge can improve without the aid of an indubitable foundation. So this is the thing that we naively had. We naively had this kind of indubitable foundation of our scientific knowledge in the kind of the external world that was just feeding numbers to us. We don't have that anymore once our models are mediating our access to the world, even in measurement. But even without that, he thinks we can have an improvement in knowledge through some sort of iterative procedure. What we have is a process in which we throw very imperfect ingredients together and manufacture something just a bit less imperfect. So I have now brought you 0 to 60 on the latest state of the art in philosophy of measurement. But coherentism, I mean, that doesn't make any sense. Who wants to be a coherentist? And I actually think that maybe even, well, definitely even Ron and Ha-Seok and other people who are swayed by these sorts of examples are looking for something more than, I mean, of course, I've not given you all the ins and outs of Ha-Seok's view, but they want to go beyond the mere epistemic iteration and maybe return to some of the things we worried about in the first place, which is, you know, what are we saying about the world when we're performing measurements? What evidentiary role do our measurement outcomes play in our theory development? And so this is what I'm calling the pragmatic turn. This is where we're getting to some stuff that's quite recent. I think both of them have only kind of gestured at in print, but they've given lots of talks recently. In the case of Ha-Seok Cheng, there's lots of talks online. So if you think this is an interesting idea, you can watch him give 6 lectures in Prague about this. But they're both pulling on ideas from pragmatism in a way that I think is kind of to try and start to tie this coherentist, this epistemic iteration view back to the world a little bit in a tempered way. And that's what I'm going to first talk about before saying I want to tie it to the world a little bit more closely. Okay, so what's wrong with this coherentism? Well, this epistemic iteration idea, which I've only described very briefly, but it's good on some scores. It looks like it explains the internal coherence of our measurement practice. Maybe there's some way to explain how it gives us progress. But I do think that the classic realist worries here do pose a problem for this view, right? So the realist says, but how was it we're able to iteratively refine these values? Isn't there some role for the world out there? What about truth? Don't we care about whether or not our measurement outcomes are true? So I think if you have these sorts of worries, then you're not going to be that happy with a purely coherentist view. So what might we say if we want to maintain this coherentist view in response to that? So I don't know that Iran would identify his view as pragmatist at all. But the sort of the latest thing he's been talking about, he's been trying to think about, okay, what exactly is the structure of this reasoning that allows us to infer from these numbers measurement outcomes? And he started to use this term inference to the best prediction as a way of kind of cashing out what is the type of inference you're doing. Say in the case of the clock case, the time case. You're looking at a bunch of numbers. You're moving by those numbers to something else that you're calling universal time. What's the structure of that inference? Inference to the best prediction. So one thing to point out is it's a type of abductive inference. It's a type of moving backwards, as it were, from effects to causes. So I like to gloss abductive inference. But it's crucially not the same as inference to the best explanation. There's something different here going on than explanation. And so we have to wait for the future Iran Tal to tell us exactly how this is going to work out. But I know he's working on it right now. Why am I calling it a pragmatic turn? Well, because abductive inference is something that comes from the greatest pragmatist of all time, in my opinion. Charles Sanders Peirce, he's the one who kind of first identifies abductive inference as a mode of reasoning. He identifies it not just as the crucial mode of scientific reasoning, but also the crucial mode of everyday reasoning. And he kind of interestingly, the way he characterizes it, it is not as inference to the best explanation. So in philosophy of science, we often talk about abduction and inference to the best explanation as if these are interchangeable ways of thinking about things. But really, inference to the best explanation is one way of cashing out abductive inference. It's one type of abductive inference. Inference to the best prediction is going to be a different type of abductive inference. And it's maybe going to have very different properties, epistemic properties. So this is just a gesture in the direction of pragmatism coming from Iran. Here's another gesture in the direction of pragmatism coming from Hassock. And Hassock is much more explicit about, pragmatism with a capital P. That's what I'm doing now, he says. And I think he is really interested in getting back to this big picture question about truth, knowledge, with a capital T, with a capital K. We want to bring these things back, but how are we going to do it building on this notion of epistemic iteration? What's the right sort of move here? And it looks like pragmatism has some sort of resources here. If you rethink your notion of truth as some sort of pragmatic notion of truth as the thing that works, the output, as it were, of successful action, then maybe you can say something, well, whatever the outcome of this iterative process is, that's just all we mean by truth. For Hassock, this ties very closely to other core commitments that he has. So he's very interested in pluralism as an idea within philosophy of science. So the idea that science could have taken another trajectory. In his last book, he talks a lot about, what if the phlogiston theorists had kept on doing research, kept on developing their theory? Actually, they could have made more and more precise measurements. They could have gone through this process of epistemic iteration. They could have explained things that Lavoisier and the oxygen theorists couldn't. They could have avoided some of the Kuhn loss that we got in that particular instance of theory change. Hassock is also very keen to reject the correspondence theory of truth. He said, this is just the wrong way of thinking about truth. And a slogan that he has is realism for realistic people. So I think his idea is actually this kind of old-fashioned, logical positivist correspondence theory of truth. That's not what we mean every day by truth anyway. That's not the sort of truth that ordinary people talk about. That's not the sort of knowledge that ordinary people talk about. Why don't we use the sort of notion of truth, the sort of notion of knowledge that matters for us in an everyday context, bring that back in contact with science? That is truth enough. If our iterative practices become more and more refined, what more do we need or want as a notion of truth? I'm resisting listing Peirce here and just listing James, and for Hassock, Dewey especially is an inspirational figure for him. Because actually, as we'll see in just a second, Peirce is one of the figures that Hassock explicitly rejects in his flavor of pragmatist turn. So here's a lovely way of kind of picturing how Hassock is thinking about things. I've recreated these images. I wasn't able to find his slides, but I've recreated them from a talk that Hassock gave here actually a couple of years ago. Oh, is it? Does he have the pictures in there too? I just didn't, Next time I give the talk, I'll use the real pictures. I'll use the real pictures. So here's one way you might think of science. There's this metaphor of science as kind of building an edifice of theory, constructing something that's ever more and more, and you've got some sort of, and so in this metaphor of science as some sort of construction or convergence towards a goal, you might think of sort of building up from the ground as somehow the notion of progress or refinement, and there's some sort of convergence, you're building towards some point. And in fact, I'm annoyed at how much the floor is creaking. I don't know what to do about that. I'd stand on the other side, but that would be too confusing. In fact, this is the notion from my favorite pragmatist, Peirce. So Peirce does in fact give a non-standard notion of truth, but his notion of truth is not actually as relativistic as maybe some other pragmatist notions of truth. He says, truth is just the opinion which is fated to be ultimately agreed to by all who investigate, is what we mean by the truth. So it's kind of nicely different if you think about it from this boring kind of Putnam-type scientific realism, because it's not about taking the current state of science as true. The truth is this kind of endpoint that you're converging at. But Hassock said, when he gave the talk, it was really extremely lovely. He said, this is this old flat Earth way of thinking about things. And we know we live on a spherical Earth now. So what happens when we think about this metaphor of science as building on a spherical Earth? Well, that's going to motivate for him this kind of pluralistic viewpoint. And the idea is supposed to be, if you recognize, you might accept this idea that science is some sort of edifice construction, but that edifice can be constructed in all kinds of different directions, and those might actually be divergent in where they're going, and yet still be equally valid, and still be able to be an endeavor that can iteratively be refined. So pluralism implies divergence rather than convergence. Equally valid research programs may follow arbitrarily different paths of epistemic iteration. So this is the Hassock-Chang worldview, which I find very suggestive. I'm very much on board with a lot of this. But it's still not close enough to the world for me. So I want to try and get back to the world just a tiny little step more. And then I've used this nasty word, transcendental, that Michaela needs to shut her eyes whenever it appears. Why? Why is this not good enough? So here are some things about our measurement practice that to me are just hallmarks of reality. There's got to be something going on with the world here. So one is just this convergence point. We are measuring a physical constant repeatedly. Interestingly, so I'm going to just quickly reference some examples that have been kind of worked to death in philosophy of science on this, just to remind people. But we can make radically different theoretical assumptions about these physical constants, and yet still converge on their value and be able to measure those values with greater and greater precision. And these outcomes, these measurement outcomes of physical constants, they remain stable across time, across changes in the measurement apparatus, across changes in theory about what the unobservables are. If you think about Newton's measurements of the regions of wavelengths of light associated with the different colors that we see and how they're triggering receptors in the eye, he doesn't even have a wave theory of light, and yet he's able to put numbers on this of some sort that are quite close to numbers we're able to later put once we have a wavelength theory of light. So there's numbers that are getting more and more precise across quite radical changes in theory about what's going on with the underlying unobservables. And yeah, our measurement outcomes are increasing in precision. So if you think about this measurement of universal time, the level of precision involved here is incredibly fine-grained. And all the physical constants now, we're routinely measuring to many, many decimal points. So for me, these are hallmarks of something beyond us that we don't just need to define away, But we've got to have a story about what exactly it is to latch onto it, how exactly we're latching onto it. So here's just some examples that have been done to death that I wanted to reference on this point. And mostly they've been discussed historically in the context of the more traditional realism question, realism about the underlying unobservables. So one example that's been discussed is J.J. Thomson's work measuring the ratio between the charge and mass of the electron. So this is back in the late 19th century. A cathode ray tube, you try and make a vacuum in a tube, and it turns out when you put an electrical current through it, you see these like flashes, this kind of beam. What the heck is this thing? People start to talk about it in terms of electrons, but they don't have any robust realist theory about electrons. And Thomson is able to measure the ratio between the mass and the charge of the electron by putting a magnetic field around this cathode ray tube while the ray is traveling through it, and looking at the way it deflects the position of the electron. And so what you have is an interaction between the charge of the electron and the way that's affected by a magnetic field, and the mass of the electron, and that can giving it momentum to go across. And the interesting thing about the example, well, there's several interesting things about it. One thing is, Thomson doesn't need to be much of a realist about the electron to do this experiment. He just needs to think that this is a number that he can measure. And he uses different experimental setups to measure it. So he passes it through a magnetic field, he passes it through an electrical field. And it's this getting convergent values across different theoretical assumptions, different experimental setups, that gives him some sense that he's latching onto some part of the world when he's giving this number to the mass-charge ratio. And that's something that's robust beyond his particular assessment of electrons as entities or as unobservables that you might have some, Putnamy, boring, old-fashioned realist kind of view about. So I'm getting some of this from George Smith's paper on Thomson, but lots of people have talked about this example. Another example that's been talked about a lot is Perrin's experiments measuring Avogadro's number. So again, a lot of the discussion on this has been in the context of the traditional realism debate and whether or not Perrin is licensed to infer the existence of molecules on the basis of his measurements of Avogadro's number. So what's Perrin doing? Einstein publishes a paper about Brownian motion, which kind of inspires this idea that you should be able to observe the pattern of motions of a particle that's big enough for you to see in a fluid and infer from that something about how often it's being struck randomly by particles too small for you to see. So Brownian motion is where a particle is suspended in a fluid and it's kind of moving around randomly. Whenever you hold your glass of water up to the light and there's like a mote of dust in it, you'll see that it kind of is doing this random walk motion. And the point is that Perrin spends 10 years and a large number of different experimental setups in order to try and measure this number. So Avogadro's number is just the number of, I found it very difficult to decide like what word to put here. Because so a mole is like a number of like units of something. So it can be atoms, it could be molecules, it could be, so stuff. There's little bits. There's bits in a mole of a substance. How many of them are there? Yeah, and of course you start getting at this from mass and weighing experiments in chemistry during the chemical revolution. Anyway, so Avogadro's number. How is this connected to Brownian motion? Well, if the motion of the mote of dust in your glass of water is caused by it being banged by little molecules of water, then you can use the statistical properties of its random walk to draw an inference about how often it's being banged, and that can allow you to draw an inference about how many molecules there are in that like lump of water. But the point of the example is, in measuring this number, Perrin is using different assumptions and different experimental setups. So sometimes, so these diagrams here, these are his actual data of particular random walks of motes of gambage under, I believe that's how you say that word, under the influence of Brownian motion in some fluid. And the point is he's taking these data points, each dot is a data point at a regular time interval, but then he can do statistical analysis on the direction and length of each step in the walk. And then he can look at whether or not it satisfies the statistical model of a random walk, and then he can infer something about how often it's being hit. So these he's getting by shining light through a glass of water and projecting it onto this graph paper on the wall, so he's able to like blow up very large, this kind of movement, a little particle. But he does other sorts of experiments where he's using sort of models of fluid movement and Navier-Stokes equations in order to model what's going on in the fluid in other ways. So he's bringing in different sorts of theoretical assumptions, and he's getting a number that he's able to measure quite precisely, and he's getting convergent values of that across these different experimental setups. So I'll just mention Deborah Mayo has talked a lot about this example in her book. Stathis Silas has a few papers about it. Of course, for Silas, he cares about this as an argument for realism about the molecules. What I care about here is the significance of this number and what it means that he's able to kind of get this number more and more precisely. And even poor Stathis, I don't know what he was thinking, but he's got this quote for Perrin in the paper where Perrin kind of says, actually we could eliminate the molecules, we don't really need them. Kind of crucial point is that we've fixed this magnitude. And he talks about the miracle of concordance across these results. So there's something miraculous about the convergence of the numbers. The numbers, the fixing the magnitude is what's really crucial. And Silas is the foot-stamping realist who wants to come along and talk about the molecules. Okay, so these are just meant to illustrate, helps if you've seen these sorts of things before, what I mean by the convergence and the precision and all that. So what are the morals here? So I think I'm happy to say, okay, those sorts of examples aren't good enough for the old-fashioned foot-stamping realism. I'm going to grant, von Frosten, yeah, your worries go through. All this shows is that those theoretical assumptions are empirically adequate. I'll grant you that. But I still think that this convergence implies realism about something. That number is latching on to, now I'm just going to use a term to stand in for the thing, but I'm going to call them fixed points of some sort. These numbers are latching on to fixed points of some sort in the world. And what might we say about these fixed points? Well, they're somehow human independent. They're going beyond our theoretical commitments. And you kind of see that by the fact that we can take very different sets of theoretical commitments and still get at them in a very precise way. These fixed points are somehow accessible by our measurement procedures. Maybe our story about how that works is going to change when our theory of the unobservables or whatever changes, but we're somehow getting, maybe it's going to be true despite the theory-ladenness of our assumptions, but somehow we're getting at something beyond them. And they're constraining what the outcome of those measurement practices are. So that's sort of what I mean by fixed points. And the fixed points are the things I think we can have as a little flavor of realism beyond the pragmatic turn of the coherentists. So why am I calling it transcendental pragmatism? Oh no, oh God. Yes, look away, look away. Okay, so I think these things, the fixity, the value, the convergence, the precision of measurement, it provides some kind of abductive support. So here I'm gonna stand with Iran. They provide some sort of abductive support for some kind of realism about values. But what I want to say is that there's something we can go beyond here, inference to the best explanation or even best prediction. I think there's some sense in which there's a kind of only explanation. The only explanation for this is something fixed beyond us. Yes, eyebrows are raised. Well, they might be, but nevertheless, that's what I'm going to say. I mean, I'm going to stand by it. And I think that's the sense in which it's somehow transcendental. It's the kind of these measurement practices are only coherent on the assumption of there being these fixed points. I don't think you can make sense of what we're doing. So in that sense, they're kind of conditions for the possibility of us getting these convergent values across changes in theory, changes in measurement device, changes in our theoretical assumptions. So that's sort of what I mean by transcendental pragmatism. I want to say, Hasok, I love your pluralism. I love spherical science. I'm all for it. But making the pluralist move doesn't mean we have to give up on this reality about the fixed points. So I think this is my schematic here of our multiple convergent fixed points. So I'm going to claim, look, just because we've got multiple research programs that diverge in the fixed points that they're aiming at, and it may even be that my research program and your research program are in some sense incommensurable. We can't even translate my way of talking about the fixed point I'm getting at to yours. Insofar as I'm engaging in one of these iterative procedures that enables to get increasing precision and fixity in my measurement outcome, then I am converging on something. I think there's this inference to the only explanation that that's what's going on. And you can have a view that has this kind of plurality of fixed points in nature. Maybe some of them are accessible through some research programs and not others, and vice versa. But it's illegitimate to infer from something like the incommensurability of these descriptions or these research programs to inconsistency in the objective world. The objective world can outstrip our ability to describe it, I think. So that's how I want to talk about the pluralism. All right, so what are the features of this view that I'm vaguely gesturing at here, but which I personally am very happy with so far, as of yesterday? So how is it pragmatist? Well, it still takes it that our actions, our abilities, our ability to measurement is what's, in some sense, determining when we have knowledge, when we have truth. We have to be engaging in these actions. And it's some form of abductive inference from these actions by which we're getting at truths about the world. These are the parts that are, in some sense, pragmatist. But the way in which it's transcendental is this idea that, but it's not an inference to a best explanation, it's an inference to the only explanation, the thing that makes those practices coherent, the conditions for the possibility of convergent measurement. It's realist in the sense that these things we're converging on are fixed points in nature independent of us, and that these measured values are corresponding to objective human independent features of the world, but it's still pluralist friendly because the fixed points that are out there for us to latch onto can outstrip the measurement practices of any one single research program. And there's no principled limit on the fixed points for us to discover. New research programs are possible to head in new directions and find new fixed points. So here's a summary. Views we've seen so far. Sorry it was all so high level. Coherentism. So this is this first pass. We notice that models are being used in measurement. What do we get to say? We get to say that knowledge is somehow the result of an iterative epistemic practice, and that gives us some sort of constructivism about the fixed points. We're somehow making the fixed points ourselves. This is the thing that von Frosten takes away from this in his representation book. Then we get this pragmatist turn, and we say, okay, wait a minute, we need to bring truth and knowledge back in, but let's just define them in terms of the measurement success. And that gives us a kind of inference to the best prediction, which is maybe something weaker than inference to the best explanation in terms of underlying unobservable causes. So maybe that's good, but it's still too weak for me. And I add this nasty T word in at the front. And the idea is supposed to be something like our practices is determining what are the targets of our investigation. But the only way to make sense of this convergence and fixing our measurement is by attributing these fixed points to the world. And it's not inference to the best explanation. It's inference to the only way to make sense of that, the only way to make that coherent. Thank you.